Hi, I am Dr. Gudmundsson. This video contains supplemental material intended for my students in my aircraft design classes at Imperial Aeronautical University, where I currently teach. The video features excerpts from my textbook, General Aviation Aircraft Design, Applied Methods and Procedures, now also available in a Chinese translation. The book is available online from a large number of outlets, including Elsevier and Amazon. It is recommended for anyone interested in the design of general aviation aircraft. Greetings! In this video I am going to show you how to prepare a basic aircraft performance analysis using Microsoft Excel. We are going to use it to extract very important performance parameters for your new airplane. There are several benefits to doing this in Excel rather than work everything out on a piece of paper. For one, we can use the setup for more than one aircraft. Second, we can actually make the analysis super accurate. And third, we can plot any combinations of parameters, which gives us a great intuitive feel for what actually takes place over the entire speed range of the aircraft. In interest of time, I am going to keep this simple, and I'm going to show you where and how the analysis may veer off course. Before we begin, I want to stress to my students watching this that in my classes I demand an appealing appearance of the spreadsheet. It has to be legible, organized, and clean. This includes using appropriate colors and presenting numbers with only reasonable significant digits. It is important to remember that as a professional engineer you will frequently make spreadsheets for others, in contrast to making one for yourself. Your work becomes a mirror to your professionalism. To help in this endeavor, never use strong colors as shown here. This burns the retina of normal people. Instead, use mild pastel colors as shown here. These are far less offensive to most people. Additionally, take advantage of Excel's formatting options that allow you to make text in sub and superscript. Also note that I have two distinct colors to represent the role of selected cells. The green cells are used by the user to enter information. The bluish cells contain formulas and should not be changed at all. Alrighty then, let's start this adventure. Open a new worksheet in Excel and prepare it as you see here. You can pause this video while you do this, and when done, continue watching. Note that I will be using Excel's native language, Visual Basic for Applications, or VBA, to write routines that are called from the spreadsheet. Therefore, make sure you have the Developers tab visible on the spreadsheet interface. Do this by selecting the File menu and locate the Options command. This opens the form you see here. Select Customize ribbon. Look for the Developer checkbox in the list to the right. Make sure it is checked. Press OK. Click on the Developer tab to access the VBA programming page. Press the Visual Basic icon to open the form that contains the code. I am not going to teach you how to write code in Visual Basic. There are plenty of tutorials on YouTube for that purpose. Rather, I am showing you how to access the code once you know how to write it. VBA adds substantial power to Excel. It will allow you, eventually, to write code for thrust and drag models that will add great accuracy to your predictions. In this session, I will use it to extract my own functions that return atmospheric properties and convert calibrated airspeed to equivalent airspeed and equivalent to true airspeed. No, I will not give you my code. If you truly want to learn this, then you must write your own routines. All the theory needed for this is given in Chapter 16 in the first edition of my textbook, General Aviation Aircraft Design, Applied Methods and Procedures, or Chapter 17 in the second edition of the book. Alrighty, let's assume we are designing a light sport aircraft, or LSA, that weighs 1,320 pounds at condition. Let's say that 200 pounds of this is fuel. Let's copy the properties of this cell to here, as I am going to enter a formula in this cell. Therefore, the weight minus the fuel weight is 1,120 pounds. Also, let's adjust the decimals here. Why, you ask? because there is no scale on Mother Earth that will accurately measure 1120 pounds to 2 decimals. Leaving the 2 decimals here shows engineering naivete. I am a professional, and I'm not going to have the user of my spreadsheet think otherwise. One of the most frequently expressed complaints leveled by people from industry interviewing student engineers is, "Why do the students show numbers with all these significant digits?" they ask. One such individual said to me, "Don't they know how amateurish this looks?" Some express losing interest in hiring such students. Luckily, the solution is simple. You only have to make sure you are not one of those students. Anyway, the wing area S is 130 square feet and wingspan B is 35 feet. This means the wing aspect ratio AR is B squared over S. This amounts to 9.42. Next, let's prepare the atmospherics. An appropriate atmospheric model is given in section 16.2 in the first edition and section 17.2 in the second edition of my book. Note that I don't want to annoy you to death by constantly saying the first edition and the second edition of my book. Therefore, for the remainder of this video, I will try and minimize it by only repeating the equation numbers in the book. The first number will always refer to the first edition and the second always to the second edition. Now look, you can see the font size in the altitude cell is much larger than the rest. This is for a reason. It makes it easier for me and the user to locate it later. It also serves as a reminder to emphasize its importance. The aircraft performance calculated here represents a snapshot at a fixed altitude. The spreadsheet only calculates steady-state performance. Now let's calculate the density ratio as a function of altitude. You can use equation 16-7 or 17-11 for this, but I am going to use my trusty VBA function that allows me to calculate this to an altitude of 278,000 feet. Having it around has saved me countless hours of work. I return to the form containing the VBA code and copy the function atmos property, including its arguments. I return to the worksheet and press the equal sign and paste it. Then I replace the argument names by clicking on the altitude cell and enter comma 2 because this tells my function to return the density ratio. Let's test this by entering, say, 25,000 feet for the altitude. Yes, it works just fine. Next, let's calculate the density. The standard day density at sea level is 0.002378 slugs per cubic foot. Thus, I multiply it by the density ratio. Done. Next, let's calculate the absolute temperature. For this, I'm going back to my trusty atmos property function, which is still on the clipboard. Type equal sign, paste, reference the altitude, and now enter 10 as property ID, as this will return the absolute temperature using the UK system. This value is 518.67 degrees Rankine at sea level. This is obtained using equations 16-2 or 17-4. We can now calculate the speed of sound at the entered altitude. It is the square root of the product R times gamma times T. R is the specific gas constant, gamma is the ratio of specific heats, and T is the absolute temperature we just calculated. This is equation 16-23 or 17-19. Now, let's assume we have completed an aerodynamic analysis of our LSA and are ready to enter the parameters listed in the second column of our spreadsheet. Here we will assume the symbology of Chapter 9, the anatomy of the wing, in both editions. First, note the video editor's curse. The 3 top descriptions are the same, discovered after taping the video. Bummer. The first description should say CL of 0 alpha and the next one lift curve slope. The third is correct. I have fixed these in the footage where I give you an opportunity to pause and prepare your spreadsheet, but for this video we'll have to proceed with this annoying bug present. Anyway, assume we expect a CL naught of 0.2. Let's assume the lift curve slope is given by equation 9-56 or 9-71. Enter 2 times pi times the aspect ratio divided by the parentheses 2 plus the square root of 4 plus aspect ratio squared, close parentheses. Assume the lift coefficient of minimum drag is 0.2 and minimum drag coefficient is 320 drag counts. Then let's calculate the Oswald's efficiency coefficient for the airplane. For aircraft in this size class, I find equation 9-89 or 9-129 generally give good results for aspect ratios less than 12. Let's enter it here. Then let's enter the lift-induced drag constant of equation 15-7 or 16-6. 1 over the product pi times AR times E. Done. Now let's focus on the power plant. A likely engine for this aircraft would be a 100 horsepower Rotax 912 or similar. Those engines have a power-specific fuel consumption of about 0.5 pounds of fuel per hour per brake horsepower. A typical propeller for this engine has a diameter of 69 inches. Here we must convert this to a unit of feet. Therefore, I'm going to enter this as 69 divided by 12, which gives 5.75 feet. The engine is rated at 100 brake horsepower at sea level. To account for altitude effect, refer to section 7.2.1 in the first edition or section 7.2.2 of the second edition of my book. The most common method to account for the power drop in normally aspirated piston engines is through the Gag and Ferrer model of equation 7-16 or 7-8. At 8,300 feet, this should be close to 0.75, which means that at a fixed throttle setting, the engine power drops to 75% of what it is at the same throttle setting at sea level. Let's calculate the actual power, which is what we will use later in the table below. Finally, in this video, we will only look at the maximum power at the given altitude. Typically, this would be at an RPM between, say, 2,500 to 2,700. Let's just say 2,500 RPM here. Of course, we can study other power settings by changing the variable P sub BHP. That's it. Now we can tackle the table below. Okay, here I'm going to start in the calibrated airspeed VCAS column. I do this because VCAS is the airspeed the pilot will reference to fly the airplane. It is the airspeed that would show up on the airplane's airspeed indicator if it were error-free. Anyway, a typical speed range for LSA aircraft ranges from 45 kCAS, which is the maximum stalling speed permitted without using flaps, to 120 kCAS, which is the maximum legally permissible airspeed for such aircraft. Therefore, I am going to bracket this range by starting the analysis at 30 kCAS and terminate it at 130 kCAS, stepping 1 knot at a time. Next, I'm going to convert the calibrated to equivalent airspeed. The practicality of this is debatable for an aircraft that flies so slowly, but I want to force my students to always do this to retain their familiarity with this step that is really necessary for faster aircraft. To do this, you will have to read up on how to treat equivalent airspeed in section 16.3 or 17.3 in the 2 book editions. I also cover this topic in my class. But in my spreadsheet, I resort to my trusty library of functions I have developed over the years. This function is simply called Aero convert kCAS to KAS. As before, I copy the function with the argument list and paste into the cell. Then I replace the arguments as shown. I expect you already know what the $signs in the cell references mean. You can toggle through all combinations by repeatedly pressing the F4 key. I repeat this for the cell containing the true airspeed. I copy-paste my function Aero convert KAS to KTAS and replace the arguments as shown. In the next column, I convert the airspeed in KTAS to feet per second by multiplying by 1.688. This is followed by calculating the Mach number. It is simply the true airspeed in feet per second divided by the sonic speed in feet per second that we calculated earlier. Next, calculate the dynamic pressure from 1/2 rho times true airspeed in feet per second squared. Now we can calculate the lift coefficient at this airspeed. It is calculated using equation 9-50 or 9-64. Here, 3 different versions are shown, and I am going to use the last form, which is why I calculated the dynamic pressure in the first place. Now, here's an important point. You see this returns a value of 3.330. This airplane has a maximum lift coefficient of, say, 1.5 clean or without flaps. We must recognize that just because we can calculate this value does not mean the airplane can generate it. This value simply means, in order to maintain level flight at 30 kCAS, the airplane would have to develop 3.33, but it can't. Therefore, all the table values between 30 to 44 kCAS represents a region in which the airplane cannot operate. In other words, the results are erroneous. So why calculate them? Well, it helps us see if we actually capture the entire airspeed envelope. It also makes the graphs more appealing. Anyway, we can now estimate an approximate angle of attack at which the airplane would have to operate to generate the lift coefficient. It is approximate because it does not account for control surface deflection required for stable flight at that airspeed. But it gives an idea about the deck angle. For this, use equation 9-52 or 9-65. Since our lift curve slope is in units of per radian, this value will be in radians, which we convert to degrees as shown. Next, let's enter the minimum drag coefficient here. This is really done in case we want to plot it. However, for detailed analysis, this value changes with airspeed and should be calculated for each speed. This is a consequence of change in Reynolds numbers, which affects the skin friction, which in turn affects the extent of separation regions and thus pressure drag. At lower angles of attack, this is captured using the appropriate form factor during drag analysis. This requires substantial effort to prepare, and if you happen to be a student in my design class, you will have to do this for the airplane you're designing. What we are doing here is to really assume the CD min represents an average, which is why there will be a constant value for all airspeeds. Anywho, here we refer to the CD min entered earlier, 320 drag counts. Next, calculate the lift-induced drag. For this, use equation 15-6 or 16-88. I write much about the accuracy of drag modeling in both editions of my book. If you're my student, I suggest you brush up on it by reading chapter 15 in the first edition or chapter 16 in the second edition of the book. Also, watch the video on this channel called Aircraft Design Tutorial: Common Mistakes in Aircraft Drag Analysis. Here we enter K times open parenthesis CL minus CL main D close parentheses squared. The next 2 columns are easy. Add CD min and CDI. And divide CL by CD. Now let's select entries in this row and double-click this little box in the lower right corner to copy-paste everything from here to the last row in the table. Now it is time to do some initial plotting. Let's select the first 2 columns by highlighting them. Select the Insert tab and then the Scatter plot. The graph is currently showing equivalent versus calibrated airspeed. Not super interesting, but let's check out other plots. Let's move the Y column to the dynamic pressure column. This is how it behaves with respect to the airspeed. As expected, it increases with the square of the airspeed. Let's check out the lift coefficient. Here's an interesting result. You can see how the lower airspeed requires gradually higher lift coefficient and that it is really quite low at very high airspeeds. This implies high angle of attack at low airspeed and low at high airspeed. You can see this here. And this is how the drag coefficient behaves, a similar shape as that of the lift coefficient. However, when we plot the lift to drag ratio, we see something very interesting. There is a distinct maximum value. The airspeed associated with this maximum is of great importance to the operation of the aircraft. This is summarized in Table 20-2 in the second edition of my book. You can see the importance of this airspeed for jet and propeller aircraft. It is also common to calculate and plot the ratio of the lift coefficient raised to the power 1.5 to the drag coefficient, and the ratio of the square root of the lift coefficient to the drag coefficient. Their importance is also highlighted in the table. I will leave it to you to add 2 columns to compute these ratios. All these relationships are derived in the book. Alrighty, let's now calculate the thrust. We do this using the method of sections 14.4.4 of the first edition or 15.4.6 of the second edition. There I present a formula for the propeller efficiency as a function of advance ratio. It is based on data that is typical of that which some propeller manufacturers provide customers. As such, the data only applies to a specific propeller and cannot, I repeat, cannot be used indiscriminately for other propellers. Other propellers have different such functions. I've tried to make this a little more assertively obvious in the second edition. That said, this function is very convenient for this demonstration. However, you must also be aware of the other thrust estimation methods in my book. Anyway, we start by calculating the advance ratio using equation 14-23 or 15-33. We can now calculate the propeller efficiency eta, presented in aforementioned sections. It is now possible to calculate the propeller thrust using equation 14-38 or 15-52. Let's copy-paste this like we did earlier using that cool copy-paste trick permitted by Excel. Let's check what these new terms look like plotted. As expected, the advance ratio is a linear function of airspeed for constant rotation rate and propeller diameter. The propeller efficiency is a quadratic function and the thrust is a slightly nonlinear function as well. All of this looks pretty reasonable, so let's move on. The drag is simply the dynamic pressure times the wing area times the drag coefficient. The power required represents the thrust power required to maintain steady, level flight at the given airspeed. Recall the definition of power. It is the time rate of change of work given by force times speed. Here the power required is the product drag times true airspeed in feet per second. The units are foot-pounds per second. The power available represents the power delivered by the engine through the propeller. A propeller generates thrust by accelerating the air inside the stream tube going through the propeller disc to an airspeed larger than the flight speed of the aircraft. We say the propeller induces an increase in the flow speed, such it moves faster than the flow speed outside of the stream tube. We call this induced speed. It is the difference between the airspeed through the propeller disc and the far-field airspeed. This acceleration absorbs a fraction of the available mechanical energy delivered by the engine. Some of it is lost due to the flow acceleration. We measure it through fruit efficiency. The rest is lost to friction that must be overcome by the rotating propeller. We measure this through viscous profile efficiency. The propeller efficiency is the product of the two. To give you an idea of what sort of speeds we're talking about, consider an airplane flying at 100 kilometers an hour. It is possible the average airspeed in the stream tube amounts to 130 kilometers an hour. Thus, the induced speed is 30 kilometers per hour. The resulting fruit efficiency would be 0.77. If the viscous efficiency was, say, 0.9 at this instant, the propeller efficiency would be 0.69. This means an engine delivering 100 horsepower would only create 69 horsepower worth of thrust power. This is what we're calculating here. So thrust power is thrust times airspeed. The excess power is simply the difference between the available and required power. If it is positive, then per equation 19-52 or 20-80, three things can happen. 1. If the airspeed is constant, then the term dv/dt is equal to 0. The airplane will increase its height or climb, and it does so whether the pilot likes it or not. 2. If the term dh/dt is 0, then the airplane will accelerate to a higher airspeed. And 3. There is a combination of 1 and 2. If the excess power is negative, then the opposite will happen. The airplane will lose altitude or decelerate, or a combination of the two. Now let's check how the drag changes with airspeed. You can see there's a distinct minimum. Let's co-plot the thrust. Here's a fast way to add another series to a graph in Excel. Click on the current curve and copy the series string from the entry box as shown here. Click somewhere on the graph to clear the entry box. Paste the series string and change the last number, the curve ID, to 2. Hit enter. The intersection of the thrust and drag forces over here represents the fastest airspeed the airplane can achieve at this altitude. There should be another intersection on the left-hand side, but it occurs at an airspeed less than the 30 kCAS. Recall that assuming our stall speed will be 45 kCAS, that prediction is altogether incorrect. It shows the limitation of the adjusted drag model that it can't keep up with the rapid rise of drag as the airspeed drops. The simplified drag model, it is much worse in this capacity. You need to be aware of this shortcoming because it leads to awful low-speed performance predictions. Fortunately, we can fix this by abandoning the quadratic representation once a specific lift coefficient is achieved, and create a spline that better approximates this high drag. I have used the quadratic spline method I present in section 15.2.3 in the first edition, or 16.2.3 in the second one. I have used it for decades with good results, although it is by no means perfect. If you're a student in my aircraft design class, you will have to employ this method in your performance predictions. Let's now add the stalling speed to this graph. It puts things in perspective for us. Let me speed this up in interest of time. So the red dashed vertical line indicates the 45 kCAS stall speed limit. The values for any airspeed below this line is invalid because the airplane is stalled. Just for the record, there are LSA aircraft out there that have a stalling speed lower than 45 kCAS. This is certainly not a problem, but for those aircraft, the red vertical line would be shifted to whatever stall speed it would be. For this exercise, I am just assuming that I am shooting for the 45 kCAS stall limit. Now let's finish the remaining columns. The ROD stands for rate of descent. It assumes the engine power is off and the airplane is in glide. Since all LSA have fixed pitch propellers, chances are the propellers would windmill in the absence of engine power. This means the drag coefficient would be increased by 150 drag counts, give or take. Thus, the glide performance would be significantly reduced. This is based on an unpublished study that I have done of a large number of general aviation aircraft. However, this calculation here assumes we have no such problem. The ROD is given by equation 2110 or 2211. V sub v in the expression stands for vertical velocity. We use a negative here because the resulting value should have a negative value to distinguish it from the rate of climb, which has a positive value. Therefore, we enter the negative of the power required divided by the weight of the airplane. The AOD stands for angle of descent. It is the glide angle. It is the inverse sine of the rate of descent divided by the airspeed in feet per second. Since we have the ROD already in the pilot-friendly feet per minute, we have to divide it by 60. Also, the inverse sine function returns the glide angle in radians. We convert it to degrees as shown. When we plot this, we can identify the best glide speed as the largest value along the curve. Remember, the values are all negative, so it is indeed the largest negative value that has the smallest magnitude. Yes, this sounds crazy, but hey, this is mathematics. The ROC stands for rate of climb. It is given by equation 18-17 or 19-18. It is the excess power divided by the weight of the airplane, multiplied by 60 to convert to feet per minute. The AOC stands for angle of climb. It is the climb angle. It is obtained in a similar manner as that of the angle of descent. The column marked E stands for endurance. For propeller aircraft, it is given by equation 20-22 or 21-69 for cruise profile number 3. The column marked R stands for range. For propeller aircraft, it is given by equation 20-12 or 21-38 for cruise profile number 3. The final two columns represent what is commonly referred to as Carson's products. Its maximum value represents cruise speed goals for jetliners. The maximum is sometimes called the fastest efficient airspeed to fly. It is given by equation 19-24 or 20-60. For more information, see section 19.2.9 in the first edition or section 20.3.9 in the second edition. Now I want to show you how to extract the most important airspeeds from this analysis work. The reason for this work is to identify the maxima and minima of selected characteristics. We do this by specifying the airspeed associated with it. When I say specifying, I mean we tell the marketing department so it can start to tell potential customers about it. We also tell the pilots about this because they need to know when they operate the airplane. What we say is that the best rate of climb is this much and it occurs at this airspeed. The best range is this far and it occurs at that airspeed. And the maximum lift to drag ratio is this much and it occurs at the other speed, and so forth. The first step is to identify the maximum and minimum of each column of interest. This is accomplished using the max and min functions as shown. The next step allows us to identify the airspeed with which the maximum or minimum is associated. This is a bit trickier, but pretty clever. We do this using the match and index functions. Let me show you how this works. I'll first show you how the match function works. I'll do it in the cell above here. Type =, match, parenthesis open. Then select whether you want to locate the maximum or minimum value. Here we are interested in the maximum lift to drag ratio, so we pick accordingly. The next argument is the vector of numbers to surge. Here, naturally, it is the entire list of lift to drag ratios. The last argument in the function is the value 0. This makes the match function return the position of the lookup value in the list. Here it returns the value 29. This value means that the maximum lift to drag ratio is the 29th value in the list, starting from the top. Next, let me show you how we use this information. We do this through the index function. What I want Excel to display here is the calibrated airspeed associated with the maximum lift to drag ratio. The index function allows me to do this. Type =, index, parenthesis open. Then select the vector of numbers in the vcast column. Next, click on the cell containing the number 29. Voila! It shows the maximum lift to drag ratio occurs when the calibrated airspeed is 58 kCAS. To make this useful, let's copy the formula that returned 29 and paste it into the index function. Now, I will copy these 3 cells and paste them on top of the other columns. Even though we want the maximum value for most of them, there are some for which we are interested in the minimum. For instance, we are interested in the minimum drag and minimum power. We must adjust the formula for VUpt accordingly for those. Okay, I have now polished the spreadsheet a little more and now want to take a look at what parameters we can extract. These can be seen here. Columns for which the maximum is important are shown in blue and corresponding minimums in red. Always compare your results to existing aircraft when you can, and you can most of the time. This is important to help identify suspicious results. Here I am comparing the spreadsheet to another LSA, the Cessna 162 Skycatcher. The data for the Skycatcher is obtained from its pilot's operating handbook. Note the differences in powerplant and propeller diameter. Parameters in red are suspicious. I'm going to call out the minimum sink rate values as incorrect because of the absence of low-speed drag correction. The best glide speed is also suspicious for the same reason. While I suspect the absence of drag splining, we must keep in mind it is also affected by CL-min-D. It too may be a contributor. The remaining data is probably reasonable. The spreadsheet aircraft has less minimum drag compared to the Skycatcher, or 320 versus 333 drag counts for the Skycatcher, per example 3-1 in the second edition of my book. The spreadsheet aircraft also has a larger aspect ratio, so the higher speed and longer range is not surprising. The Skycatcher climbs a little bit better than the spreadsheet aircraft. Well, we have come to the end of this analysis. I hope it has been helpful to you. If so, I hope you will show your appreciation by liking the video and subscribing. Have fun designing.